Hello everyone, hope you're doing well. Welcome back to my channel. Once again, congratulations everyone. We are just one day away from getting the badge for the November Daily Code Challenge. If we have been consistent till here, really congratulations to all of you. Really heads up to all of you. Today's question again, hard question. Yesterday also we had a similar question, exactly similar question, exact similar approach also, but that was also hard and this is also hard. And if you are following this whole November Daily Code Challenge, let me tell you that this is the fourth hard question that we are getting in the November Daily Code Challenge. Okay, and there is just one day to go. So let us see this question. It's very similar to what we saw yesterday. So if you have not seen yesterday's question, please see that once because it's exactly same. Okay, I can say that it's exactly same. Yesterday's I would say that that was bit more complex to apply the algorithm, like apply to understand the use case if this can be applied, if this use can solve in a graph or not. But in this it's very clear that we have to solve it in the graph. Okay, so again this is exactly, you can say, like both yesterday's question and this question are like you can say almost similar in nature. Okay, they are like one after the another. Okay, so if you have not seen yesterday's question, just go and try that out. That was also a hard question and that was also on a graph. Okay, and this is, I think, the sixth day that we are getting a question on graph. So if you have not been following us, we can go through the last 6 days of the Real Code Challenge and follow those questions. They're really nice questions. Okay, we started from a very basic level, now we are coming to the hard level of graphs. So let us begin with today's question. It's 2577. Minimum time to visit a cell in a grid. Okay, so let's see the question first. If you see, again the same thing, we are given a grid basically. In this case, so yesterday what happened, like it was a binary one. This is not a binary one basically. This is actually a grid and it has all the positive numbers. Okay, and we have to ultimately return an integer answer. Okay, before that let's see the constraints first. You see the constraints slightly better than yesterday's case. Yesterday the constraints were even worse. Okay, they were up to 10 by 5 for each dimension. Here in this case, each direct, that is each dimension, will be almost 1000, which is 10 power 3, which is less than yesterday's one. Okay, and okay, fine. Yeah, there is nothing much to look in this, and the only thing that I wanted to show is that all the elements in the grid are going to be positive. Okay, that is something that I want to show in the start of the question itself. Okay, now let's begin with the question. You are given with the m cross n matrix. One thing is clear, it's not a square matrix. Okay, which they are calling as a grid consisting of non-negative integers where grid of row comma column, that is grid of, say, you can say x comma y, represent the minimum time required to be able to visit that cell, row comma column. And one more thing, friends, like if you feel that you have seen this question somewhere, let me remind you that, I think 1 or 2 weeks back, the exact similar question, you can say almost same question, came in the Sunday daily, that is weekly challenge. Okay, the weekly contest that we had on Sunday. This was one of the, say, question number 3 in that. Okay, because it was medium but on a higher side. So this was the question number 3 in that contest, which happened on Sunday. Okay, I think 1 or 2 weeks back. So this is exactly the same, almost the same, you can say. Fine. So what they're saying, yeah, so each value in with this grid, okay, what are the differences? They are saying to say that only if the time is greater than that or equal to that, only then you can visit the cell. Okay, so they are saying that, yeah, grid of row comma column represents the minimum time required to be able to visit the cell. Okay, which means you can visit this particular cell only when the time you visit is greater than or equal to this, the value of this. Okay, so the idea is, for example, if you say the, for example, 0 comma 1 is 1. Okay, you can say 0 comma 2 is 3, which means I can visit the 0 comma 2 cell only when the time is greater than or equal to 3. Okay, that is something that you have to remember. We'll come to that what it means when we see the examples, but for now you have to understand that it's not like we can see previously what we treated is, we treated them as a weight of the edge. Okay, we treated it like that. In this case, that is not going to be the case. Why? Because we'll have to wait for some time. Okay, and only when the time, see, waiting basically means it's slightly different from the question that we have to use. Okay, what here is that they are saying you cannot stick to a cell. Okay, you cannot stick to a cell and like let the time pass. It's not like that. You'll have to keep going to adjacent elements if you have to pass the time. Okay, there is no such case that you can simply stick to a cell and pass the time. Okay, just you have to remember that fact. Yeah, fine. Which means, yeah, you can visit the cell only when the time is greater than the value mentioned in that particular cell. Okay, you're standing to the top left cell, that is 0 comma 0 cell. You're standing in that at the 0th second, and you must move to any adjacent cell in the 4 directions. Okay, each move can make so each move basically takes 1 second. That's what they're trying to say. See, this part is very important. See, we have to start with 0 comma 0 cell at the 0th second. First thing. Second thing is, you must move. You must move to any adjacent cell. Okay. The idea here is you cannot remain at one cell. Okay, and let the time pass. That is not allowed here. You have to keep moving to a cell, even if you're like waiting for some time to pass to move to the next cell. Still, you have to at least move back and forth. Okay, that is the basic idea. Remember, this part is very important because if you see when you come to example 2, you will understand that this is going to form a edge case basically. Okay, we'll see to that. Okay. Fine. Return the minimum time required in which you can visit the bottom right cell. Okay, that is the last bottom right cell. If you cannot visit the bottom right cell, return a -1. Okay, so this part what I told and this part. Okay, these two total combined will form a edge case. Okay, these two things will be combined and will be forming edge case. We'll see to that. First, let us go to example 1, example 2. In this case, what you're saying is, see, we are starting at 0 comma 0, right? And the time is t equal to 0. Now, what are the adjacent cells for it? See, always the 0 comma 0 cell will have only two adjacent cells, okay? One to the right of it and one to the bottom of it, okay? In this case, none of them is 1, okay? So idea here is, see, I cannot move to any other cell first of all. Okay, and the idea here is at each second I should move to some cell. Okay, but here that is not possible because I'm 0 comma 0. I cannot move to the cell toward the right and cannot move to cell toward the bottom. Why? See, here it is t equal to 2. That is currently I'm at t equal to 0. I have to wait for 2 seconds to be able to go to 0 comma 1. Do you agree with me? Similarly, for the case for 1 comma 0, the t has to be t equal to 3 to move to that cell. But the idea here is I cannot sit at the 0 comma 0 and let the time pass. Okay, that is not allowed. So that is the reason why the answer is going to be -1. So this is what I was talking about when I was saying this. Okay, see this part. These two things combined. Okay, you must move to any cell. Okay, that is the first thing. And the other thing is, if you cannot visit, if you cannot move, you'll have to return -1. That is the thing. Okay, so that is important. Now coming to example one. Example when we very generic case. So you can go through it. See, it's a very big one. I will not go through everything. So I will just tell you the idea. So the idea is very simple. See, you will start at 0 comma 0. One thing that I want to show before is that, see, always the 0 comma 0 cell has a value of 0. Okay, that is, we will always be starting from the 0 comma 0 cell. Okay, at t equal to 0. Just to be mindful of that fact. Okay, let me zoom in again and let us discuss the example one. See, you okay, you are at 0 comma 0 and the value is 0. Okay, now the next cell. Okay, so see, always for the 0 comma 0 cell there are only two adjacent cells. What are they? The one towards the right, which is 1, that is 0 comma 1, and the one below it, okay, which is 1 comma 0. Okay, in this case 1 comma 0 is 5. Okay, that is not possible. But let us see the next one. Here the 0 comma 1 cell has the value of 1. That means from 0 comma 0 I can move to 0 comma 1, because see, the movement will take 1 second, remember that. So once by the time I reach 0 comma 1, the time will already be equal to 1. Okay, remember that. That is the reason why we can enter this cell. So that is the basic idea, right? Once I enter this cell, okay, then I have to see what I can do. See, the idea here is very simple. See, once I reach any, say, the idea here is once I reach 0, then 1, we'll discuss this case. Okay, I've done the testing for this. Once see, I can either go below or I can go to 3. Okay, so we'll discuss this part. Let us go to that first. Okay, so you can, I'm not doing the actual tracing of example one. I'm just telling you the two cases that can arise. Okay, so let me zoom in. Let us begin. So I hope the screen is not clearly visible to see. I'm taking a small part of example one. Okay, let us say this is the matrix. Okay, let me remove the comments so that you can have a better idea. Yeah. So this is a small part of the example one matrix I've taken you. Okay. So idea is very simple. Let's say I am at 0 and then I travel towards 1. Okay. Now from 1 I want to go towards 3. Okay. Let us say that just for assumption. I understand that you can say that why you want to go from 1 to 3. Okay. You could have done from 1. You can go to this particular one. That is true, but you have to see, consider all cases, right? So just I want to teach you a case. For that reason I'm saying I have traveled 0 and 1. Next I want to go to 3. So what will happen? I'm just want to show you. See, I am traveled from 0 and then I went towards 1. Okay, this is the part that I've covered. Now the case is that by the time I reach here, the time is t equal to 1. Okay, but to cross this I have to either reach it here at t equal to 3. That is the minimum time. Okay, so the idea here is I will have to go back to 0. So that's what I'm doing. From 0 I will come back to 1. From 1 I will again go back to 0, and then again I will come back to 1. Okay, then I can cross to 3. Okay, let's see how much time it is taking. From 0 to 1, t equal to 1 we are reaching. Okay, then from back to 0, t equal to 2 we are reaching. Okay, then from 0 back to this, at t equal to 3 we are reaching. So we are at 1 again at t equal to 3, and then we are going to this particular value which is at t equal to 4. Okay, so by the time we reach 0 comma 2, which is the value 3, the t will be 4. Okay, so that is something that I want to tell you. Okay, so in case if you are here and if you see a value which is greater than the current time, this is how you will have to do. You will have to basically move back and forth. Okay, till you pass the time. So you have to pass the time, you have to move back and forth. Okay, that is the basic idea. Okay, so in this case what is happening, the value of this +1 is the t at which we are reaching that. Remember that, because in our code also I'm going to implement that. Okay, let's see the other case now. The other case is exactly same, but in this case, instead of 3, what I've done is I've kept 4. Okay, let's see how the code behaves in this case. Here also same thing is going to happen. From 0, I will go to 1. From 1 again, I will go back to 0, and then I will come back to 1, and then we'll move back to 4. Okay, so t equal to 0, t equal to 1. Okay, now I'm at t equal to 1. Okay, from 1, I will again move back to t equal to 0, which is t equal to 2. From 0 again, I will move back to 1, which is t equal to 3. And from 1, I will go back to 3, which is t equal to 4. So in this case, the value of this particular cell and the value of t is exactly same. That is, by the time I reach here, the value of t is exactly same as that of a grid of value. Okay, grid value of this particular cell. Okay, it is grid of 0 comma 2. Okay, but in this case what happened here, the time at which I reached is basically grid value of this plus 1, okay, grid value of 0 comma 2 plus 1, okay, which is at t equal to 4. So the same thing I'm going to implement in my code, okay. So that is something that we'll have to understand in this question, okay. That is the only thing that we have to spend some time on, which is slightly different from yesterday's question, okay. Otherwise the whole question is same. So what we are going to do, we are again going to use the Dijkstra's algorithm, okay. So if you are not aware of this algorithm, basically this gives the shortest path to all nodes from the source, okay. You have to determine a source. From that source it will basically give the shortest path to all the nodes, okay. Because of this algorithm, I'm going to use a heap. The only difference between this and BFS is that in BFS we basically use a queue. Here we are going to use a heap. Okay. So let's see the question now. First of all, I am capturing the dimensions of it. Okay. Let me move the example on first here. Then what I'm checking, see, this is going to be the edge case. That's what I talked about. Okay. The idea here is when we are in the zeroth cell. Okay. We have only two adjacent cells. Okay. What are they? They are 0 comma 1. Okay. Which I marked here, and they are 1 comma 0. Okay. These are the two adjacent cells that we have for when we are at 0 comma 0. Okay. The idea here is if I cannot move to them, okay, that is the grid value of them is greater than 1. Remember, if the grid value is 0, that is fine. If the grid value is 1, that is also fine. But if for both of them the grid value is greater than 1, then we have to return -1 as the answer. This is going to be the first edge case. Remember, example 2 was all about it. Okay, the all about example 2 is this. Okay, example 2 you can solve with this code itself, this much code itself. Okay, that is the basic idea. Because understand what I showed you here is, here this is possible, that is going back and forth is possible because we have more than two elements. Okay, that is zeroth element and the first element we have. Okay, we have these two elements, that's why we can go, keep moving, forward and backward. But when we have only single element, okay, when we have only single element, that is like this, we cannot go backward and move forward, right? Because we have only single element. Okay, so that is the reason why the adjacent elements of the 0 comma 0 has to be either at least one of them has to be either 0 or a 1. If both of them are greater than 1, then the answer is not possible. You have to return -1. Okay, that is one of the edge cases. Okay, now let's move next. The other thing is, because in this case, okay, a particular node will have only four neighbors. Okay, because it's a matrix, right? So here only four directions are there. Okay, for that reason, even in the question they have mentioned this basically. Okay, up, left, they have mentioned that. Okay, directions up, down, left, right. Okay, so that is the reason why, for that reason I'm again going to use the directions like this. Okay, so basically this tells me that I have to move right, I have to move left, I have to move up, I have to move down. Okay, these are the ones. Next take, see, I will give you two approaches in this question. Okay, so this is the first approach in which we are using a basically matrix to store the shortest path to reach a particular node, and in the other example I will show you basically a set to do the same. Okay, but in the approach one, what I'm showing you is I am basically using a I'm using 2D matrix again, whose dimension is same as that of my grid, to store the shortest time to reach the node. Okay? And our answer will be this: shortest time to reach the node. The same matrix, I'm just going to pick this particular element and I have to return. Okay, that is going to be our answer. Okay, that's what it is. Let me just comment this part out so that when I give the solution to you in the description, it is already commented. Okay, fine. So I hope you understand this. See, you have to refer to yesterday's question to understand this. Okay, since I've given this a detail in, explained this in detail in yesterday's question, I'm not going to do the same here. Okay, because it will take again a lot of time. This basically acts as a shortest path. What happens here is I will refer this before doing any update. Okay, so if I reach a particular node whose path, whose okay, you can say the time is greater than the time mentioned for that element in this particular matrix, then I will not explore that. Okay, as simple as that. Then what I'm doing, I'm just just manually updating this value. Okay, because always for the zeroth element the shortest time to reach will be 0 only. Okay, as simple as that. Then I'm creating a heap. Basically I'm going to use the heap. This is the first element of my heap. Okay, so what is it's going to tell me? It's going to tell me time at which we are reaching this particular node. This is the first element. Okay, the second part of this is are two things, okay, which are x and y coordinates. Okay, they are the x and y coordinates. That is for 0 comma 0 I reached at t equal to 0. That is the idea that I'm trying to convey. Now, till the heap is not empty, I have to run this loop. Okay, what is that? Let's see. First of all, I'm doing a heap pop. Okay, heap pop will give me the element which has the minimum time to reach. Okay, that is reached at the smallest possible time among all the elements in the queue. Okay, so remember, always the sorting will happen based on this. That is always the element which has the smallest time at which we reach that will be popped out. Okay, so I'm storing the current time here and I'm storing the x and y here of the popped element. Fine. See, these are some of the optimizations. You thought that also your code will work, but remember, these are just some of the optimizations. I will come to that later, but just here, what is happening is, see, heap basically it will pop out whenever the element has the smallest time among all the elements. Okay, for that reason, let us say the popped element has the coordinates of n minus 1 and m minus 1. In that case, what is the time it we have to return that. Okay, because that's going to be the answer. I don't have to follow the rest of the code. Okay, what is the rest of the code doing is basically going through its neighbor and inserting them in the queue. I don't have to do that. Once I reach here, I can return it, because remember, heap pop ensure that I only the smallest element is written. So whenever it is written, this is going to the smallest. Okay, even without that, I basically written here also. Okay, if you see, once I come out of the value, also I'm returning that. But this is the optimization. Okay, there's something that I did not show you yesterday, but just I wanted to show you today. Okay, this optimization. This is another approximation, but I will come to this later. Okay, in this question this may not be very relevant, but this is another approximation, but we'll skip it for now. Okay, so let us start the question first. Okay, for what we are doing, see, we have a node popped out, right? What is the next thing? We are going to all the directions. Then we are this basically double x and double y are going to be all the neighbors of the current element. Okay, all the neighbors of x and y. Fine. What we are doing next? We are just checking whether double x and double y are within the range of the grid or not. If they are within the range, what we are doing? First of all, we are doing current time plus one. Okay, just a second. Yeah, what we are doing current time plus one. Why? Remember, to move from one node to a direction node, we are basically requiring 1 second of time. Okay, that's why I'm doing current time plus one, and this is going to be the time at which the node is reached. Okay, this is going to be that. Then what I'm checking whether the time at which node is reached is less than this or not. If it's less than this, basically means I have to wait for some time. Okay, this if this condition is true, this indicates that I have to wait for some time. Okay, I've already explained these two cases. I'm just going to apply them now. Okay, these are the two cases that we have to apply. Okay, what I'm going to see, this is if this is true, that means there is some waiting time involved. Okay, I will keep moving back and forth to pass that waiting time. Sorry. What I'm doing, I'm taking a diff. Okay, what is the diff? This diff will tell me how much second I have to pass. Okay, to before reaching the next node. Okay, grade of x double y. This is the time at which we should enter the node, and this is the time at currently we are at. Okay, so I'm going to subtract them. If this diff is odd, if this is diff is odd, what we have to do? We have to just take grid of a double x plus one and add one to it. Okay, the way we saw here. Okay, here the value is 3, but we are reaching that at t equal to 4. Okay, so that is the reason why we have to add 1. So that's what I'm doing here. Time at which node is reached is equal to grid of that value. That is the you have to go to the grid matrix and take the value of that index and add 1 to it. Okay, as simple as that. Fine. Otherwise, if this is even, okay, what you have to do? You have to simply assign the value. Okay, time at which node is reached is equal to the grid value of that. Okay, you have to go to the grid matrix and assign the same value for that particular index. As simple as that. Okay, so this part, how I am doing it, I've already explained in the two cases. Okay, these are the two cases I've already explained. Here it is 3, we are adding 1 to it, and we are getting 4. Okay, here it is already 4, so we are taking 4 as it is. Okay, as simple as that. Fine. Next is very important part. See, this ensures that I do not go back to a node which is already wasted. Okay, so what I'm checking, the time at which the node is reached. Okay, so I'm just checking whether it is less than the shortest time. That is for, see, I mentioned, right, I've created this particular matrix. Okay, here basically all the elements are having float of infinite initially, so I'm just checking whether the current time at which I'm reaching this node is shorter than the time registered in this particular matrix for that index. Okay, if it is shorter, only then I will update this time first of all, and then I will do a heap push. That is, I'm pushing a new element to the heap. Okay, this is the heap, and this is the new element that I'm pushing. What is that? I am pushing this. Okay, the shortest time to which we are reaching the node, that is the value of this. Okay, the value of this in this particular matrix, the shortest time to reach the matrix, the value of that for this index. Okay, this is the whole one thing, right? And then the index of that, is double x and double y. Okay, this is the element that I'm going to push. Okay, and yeah, this while loop will keep continuing. Okay, and these are some optimization that I've already mentioned. Okay, and this optimization basically this ensures that, let us say, okay, this will not be useful in this case. Okay, but yeah, in yesterday's question this was useful. Okay, so this will just check that, because see, this will involve this will help us with the idea that if a value is already updated, okay, with a new value, we should not be using the old value, right? So we are just checking if the current time is greater than the shortest time to reach. Okay, let's say the shortest time got updated in between, so this the value was old one, because remember, this heap is basically bringing the smallest one forward. Okay, so this could happen that we are pushing a value which is smaller, even if the value already had that particular node already had a value which is higher. So that will come later on. To avoid exploration for that node, we are just using this. Okay, this is not useful in this case, but remember that. And finally, this is returning it, but remember, this return will not be executed. I'm just writing it to show you, because we had optimization here. This optimization will ensure that the answer is returned. Okay, I can just run this and show you how it works. I can do the tracing for example one. So we are at example one. Just see here what happens. So see, these are the basic various values. Okay, this tells me the shortest path, that is the shortest time to reach that node. Okay, from source. What is the source? Source 0, 0. For 0, 0, we can reach at 0. Okay, for 0, 1, we can reach at t equal 1. For 0, 2, we can reach at t equal 4. Okay, see, this particular 3 is there, right? That's why I mentioned at t equal 4 we can reach that, and same is the case here. So basically, if you're trying to get the answer, okay, for example one, what you can do is this from 0, 0, start moving towards the right. Okay, cross all the elements towards the right, and then from this last element, okay, that is the last element of this row, start moving towards the down. Okay, towards the downward direction, you will reach the answer, and t equal to 7. So that is the answer that I'm going to show you. So this is how it will happen. At 0, 0, we are starting, we are reaching the second, the right adjacent node. Okay, then we have to wait some time, we have to keep moving between these two elements. Okay, while We have to keep moving between these two elements while then. Okay, then we're reaching the third element, okay, which is at index 2, and then we're reaching the fourth element, which is index 3. Okay, after that I will start moving downwards. Okay, I am reaching the element below that at t equal to 6. I'm reaching the target element t equal to 7. This you can follow. There are other route also. The example, the solution which they have mentioned, they are not following this route, they're following different route, but the answer is going to be same. Okay, what they're doing is from 0 they're moving to 1 and then going to 1 below that. Okay, they're doing that, but what I'm telling you is from 0 start moving towards the right to the extreme right and start moving towards the bottom from that. So that is the answer. For example, I've already mentioned it's a edge case. Okay, here we are not exploring that. You have to return -1 in the starting itself. Okay, I've already submitted the solution and it got accepted. I've already shown you two optimizations here, which you can use whenever you are using the Dijkstra's algorithm. Okay, coming to space and time complexity. See, since we are using a grid, sorry, since we're using a matrix whose dimension is same as that of grid, so basically the space will be of M into n. Okay, coming to the time complexity, you have to understand one fact that if you see here, basically, see, this will ensure that I do not visit a node which is already visited and has a better way. Okay, so we are not. So idea here is at most, okay, a particular element will be pushed and popped only once, as simple as that. Okay, at max only once. In this case, I am telling you. So at the worst case, my queue, that is, sorry, not my queue, my heap will have all the elements. Okay, that is of m into n. Okay, total elements are going to m into n. Okay, so for a heap, okay, to do a push and pop operation, if the size is already m into n, the time of that will be needed is log m into n. Okay, so in the worst case, this much operations will have to do. Okay, see, this is the time that is going to be required when to do a push and pop when the heap has m into n elements. Okay, now since at max the heap can only have m into n elements, that is fine. Other than that, see, at max we are doing a push and pop for each element. Okay, we are not doing beyond that. So that is the reason why for m into n elements we have to keep doing the push and pop, and that will take this much time. Okay, just a second. Yeah, that will take this much time basically. So this is the space and time complexity I have for this. So yeah, and that's all for today. This question is exactly same as that of the previous question, but yeah, one thing you should be proud that you are now able to solve within a week hard questions of graph. Okay, because remember we started from very basic things. Now we are reaching a place where we are able to solve the hard questions. Okay, remember this is the level of graphs. There are more harder levels also, but yeah, still as you can see, this is marked hard, and still you are able to solve it using very simple approaches. We did not do anything, hybrid or something like that. We're using just the algorithm, small modification, and we're able to solve it. So yeah, and that was all for today. If you like my efforts, please do subscribe to my channel. This really gives a lot of motivation to continue further. Thanks a lot. Hope you will subscribe. See you tomorrow.